Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the lecture 41 of induction motors. So today we will discuss about the equivalent circuit which will be almost similar to transformers, or we will make it similar to transformer for our own analysis purpose. Okay, we will see how is it similar to transformers and why does it differ from a transformer. Also, we will do the solutions. We had asked few questions in the previous lecture. Also, we will take few questions in this lecture and we will understand the relative motion even better in today's lecture. So in the previous lecture, I gave you two homeworks. So I asked you two questions. If I have this like arrangement here, I have a stator whose stator magnetic field speed is given as ns, okay, and I have a rotor speed is nr with respect to a stationary observer. So what will be the relative speed of the rotor magnetic field with respect to stator? It's very simple. Stator is what? So whenever you have to find the relative speed, right? Relative V relative will be equals to VA minus VB. So what is VA? Like you have to find out VAB relative, right? VAB relative. So speed of A with respect to B. So what is like basically what is VAB relative? VAB relative is relative speed this is just class 11 physics, relative speed of object A with respect to object B. Okay, so it will be simply VA minus VB. Now what is VA and VB? So VA is basically the speed of object A with respect to a stationary observer, okay, or with respect to any common guy, with respect to like speed of A. If I am not mentioning anything, that means it is with respect to a stationary object. Okay, same for VB. So VB will be the speed of B with respect to any stationary object. So you can flip it as well. You can say speed of VA can be speed of A with respect to a object C, and VB will be speed of B with respect to a object C. That also you can do, because ultimately if you take the difference, right, that common point go away, right? So it is just like potential difference. So what does potential difference means? So if I have, let's say, this potential is 1 volt here, this is R1, and let's say this is R2, and let's say this potential is 2 volts, and here I have some circuit. I have here I have some network. I am not drawing the network, and this potential is 2 volts. Okay, so 2 volts with respect to what? With respect to a common ground, right? But if I am talking about the reference point, it does not matter what is the common ground, because it will be the difference, right? If I take the difference, automatically the common point will go away, right? So it will be basically 2 minus 1, that is 1 volt. Same is happening over here. So in the first case, if they are asking me the relative speed of rotor magnetic field with respect to stator, what will be the relative speed of rotor magnetic field with respect to stator? So what is the speed of the rotor magnetic field with respect to a stationary object? So speed of rotor magnetic field is basically ns, right? Because magnetic locking happens. What is the speed of a stator with respect to a stationary object? It is just stationary, right? What is the speed of the stator? So this is nrmf, ns stator, right? Is the stator rotating? Stator is, as the name suggests, it is static, it is not moving, so its speed is zero only. So if I have to find out the relative speed of rotor magnetic field with respect to stator, basically they are asking me the speed of rotor magnetic field. Indirectly, they are asking me the speed of rotor magnetic field, that is ns only. So this will be the first answer. Now the second one. Second one, if I see relative speed of stator magnetic field with respect to rotor. What is the relative speed of stator magnetic field with respect to rotor? So remember, what is the speed of the stator magnetic field? So what is the speed of stator magnetic field, it is simply ns, right? Stator magnetic field speed will be ns with respect to a stationary observer. What is the speed of the rotor with respect to a stationary observer? Speed of rotor, speed of rotor is basically nr, right? It is not a magnetic field, please keep this in mind, it is nr. So what will be the relative speed of the stator and magnetic field with respect to the rotor? It will simply be ns minus nr, right? With respect to rotor, what is the speed of the stator magnetic field? Basically, at what speed the rotor is observing, the stator magnetic field is rotating. For a stationary observer, I am observing that the stator magnetic field is rotating at ns speed. But for a moving object like the rotor, it is not observing that the stator magnetic field is moving with a speed ns. No. Same thing, if I have a box over here, right? If this box is moving with 10 meter per second, and if this box here is moving with 5 meter per second. So with respect to a stationary observer, that observer will see that this blue box is moving with 10 meter per second, this yellow box is moving by 5 meter per second. But if I am on this, if I am on this blue box, then what will be the, sorry, if I am on this yellow box, if this person is on this yellow box, then what will be the speed of the blue box? Then what will this person observe? This person will observe that it is not actually moving with 10 meter per second. This person, because this box itself is moving ahead by 5 meter per second, this person will observe the difference. That is, he will observe that box is moving by 5 meter per second, because this box itself is moving by 5 meter per second. So it will be 10 minus 5, that is 5 meter per second. Okay, but in reality, what is the reality? Reality is this is moving with 10 meter per second, this is moving with 5 meter per second with respect to a reference stationary object in the earth, this person, right? But if I am sitting here, my reference point has changed. It is just like JEE physics, right? If my reference point has changed, then what will this guy observe? This guy will observe that this is actually moving with 5 meter per second, because this box, this guy itself is moving by 5 meter per second, right? So I have to subtract that speed. That's why it is 5 meter per second. Same thing is happening here, that if I am sitting on the rotor, then what will the rotor observe? By what speed the stator magnetic field is moving? It is not moving with ns, it is ns minus nr. So I hope now finally this relative speed concept is clear, because I know, like, I have explained this previously as well. Maybe it wasn't clear that time, but now I hope it is clear right now. Okay. So yeah, that was the solution. Here this will be the second answer, ns minus nr. These will be the two answers basically. Okay, now let's move on to today's topic. Like, same things we will discuss today only, the same thing only, that we will discuss the cases, right? So special cases. This scenario explores the transformer analogy. So it is just like a transformer, but it is a rotating transformer, right? Induction motor is just like a transformer, but it is a rotating transformer. Why is it not exactly a transformer? Because if it is blocked, if the rotor is blocked, then the frequency of the rotor and the frequency of the stator is same. But if nr is not equal to 0, then f2 is not equals to f, hence it is not exactly like a transformer. It is kind of similar to a transformer, because here also mutual induction happens. Okay, so if its terminals are open circuited, then it will behave as a transformer. Okay, otherwise it will not behave as a transformer, because nr will be 0, right? Yeah, this was the synchronous speed and all those things. So there are few cases. So this is the first case. And what is the first case? In the first case, I say rotor rotates in the same direction as stator's rotating magnetic field. If I say, let's say, if first of all, keep this in mind that the rotor windings are open circuited, and I myself am rotating with my own hands. Okay, I myself am using my own hands to rotate. Let's say the stator magnetic field is rotating in the clockwise direction with speed ns, but I am moving in anti-clockwise direction with speed nr, right? Remember, this is what I am doing with my hand, because remember, rotor windings are open circuited. If rotor windings are open circuited, there will not be any torque generation. There will not be any torque generation at all. Okay. Okay. So now we have already discussed, okay, it is rotating in the same direction, so not in the opposite one we will discuss. For now it is rotating in the same direction. If it is rotating in the same direction, then what is the relative speed? We had just derived the relative speed between the stator and rotor, right? Stator field and rotor, just derived, it is ns minus nr, just derive it, right? So one thing we know, so what will be the frequency of the induced EMF? So this formula we know, right? Simple formula, that n equals to 120 f by p, correct? So from here I can find out what is my f. F will be n into p divided by 120. Now in this case, right, n is what? N is the speed at which the flux cuts the conductors. So n is what? N is actually, it is not exactly equals to n, it is n relative. It is a relative speed between the magnetic field and the rotor, right? It is n relative, it is not exactly equals to n, it is n relative. N relative is the relative speed between the rotor, between the stator magnetic field, because the stator magnetic field will cut the rotor, right? So between the, okay, I will write this in bottom. Okay, and the rotor. So this is the important formula. So that's how this came, right? So f2 will be what? The frequency of the induced EMF in the rotor will be p by 120, as I have written over here, into the relative speed. In this case the relative speed is ns minus nr if both the rotor and the stator is rotating in the same direction. Okay, remember it is open circuited, right? Now if let's say they rotate in the opposite direction, what will happen? If they rotate in the opposite direction, if they rotate in the opposite direction, so if my stator magnetic field is rotating in the clockwise direction ns and my rotor is rotating in the anti-clockwise direction nr, okay, now what is the relative speed? What is the relative speed? Like I will take another analogy. Let me take a box, okay, that is moving with 10 meter per second on the right hand side. I will take a ball that is moving on the left with 5 meter per second on the left hand side. Can you tell me what is the relative speed? For those who have already answered 15, you are correct, right? Why? Because relative speed means how far they have moved with respect to each other. Let's assume for a second, in a second, right? In a second, how far this has moved? Let's assume that this is the origin. So from the origin, this has moved by 10 meters. From the origin, the this ball, pink ball, has moved by 5 meters. So overall, what is the distance? Here it is origin, this is 5 meters and this is 10 meters, right? So this is 5 meters, this is 10 meters, okay? So overall, in 1 second, how much they have moved? In 1 second, they have moved a total of 50 meters. So what is the relative speed? It is meter per second, right? So in 1 second, if they move 50 meters, what is the relative velocity? It is 15 by 1 second, 15 meter by 1 second. So it will be 15 meter per second. That is the relative speed of the this rotor and stuff, right? So that's why we will add, right? We will add the speeds, we will not subtract. That's why here the relative speed is added, it is not subtracted. N relative will be ns plus nr because they are moving in the opposite direction, so they will cross each other more number of times because they are like, because this is circle, right? It's not a linear motion, they will cross, right? So that's why it is moving here, it is moving here, so they will reach each other much faster. If both of them moved in the same direction, maybe the cutting would not have happened so often. Now as they are moving in the opposite direction, the cutting will happen more often. Okay, that's why there is more flux to cut, that's why the frequency is higher, that's why the frequency is higher. Okay, I hope this point is clear to you guys. Okay, so yeah, this is a special case often used in understanding the frequency behavior of rotor currents, especially in testing scenario. Sometimes we want to test and dynamically simulate the rotor, right? So in those kind of cases, we open circuit the rotor terminals. That can only be done in wound rotor, it cannot be done in squirrel cage, right? So this concept demonstrates how induction machine can act like a transformer. Okay, uh, but remember, it is not exactly like a transformer because the frequency is different. Okay, similar to a transformer, okay, with rotating secondary. So I hope you have understood, like this is the summary basically. Now let's do a question and we will try to understand it even further. A 4-pole 3-phase induction machine has its stator connected to a 3-phase 50 hertz supply. So the supply is 50 hertz, it is a 4-pole machine, so number of poles is 4. The rotor is driven by an external prime mover at 750 rpm. So rotor NR is 750 rpm. Rotor speed is 750 rpm. With its, remember, you have to always look for this statement that the slip rings must be open, right? If the slip rings are not open, that means it will, like, something weird will happen because current will flow. If current flows, it will generate a torque. That is a bad thing, right? So whatever we have discussed is with respect to the rotor terminals being open, no current flows. What is the frequency of the voltage induced across any of the two slip rings? So frequency is very simple, right? Frequency is what? Frequency is n relative. So P divided by 120 into n relative, right? So I know P, I know 120. What is n relative? N relative. Now remember here, right? Driven by an external. So here, right, they have not mentioned in which direction they are rotating it. Nothing is mentioned in which direction they are rotating it, right? So what I will do, I will assume two cases. So case one, because they have not mentioned, it is a objective, it is a subjective type question. So case one, if both the rotor and stator magnetic field rotate in same direction. Okay. So if this happens, then what is my n relative? N relative will be ns minus nr. So my, so what is my ns? So I will first of all derive my ns. What is ns? Ns, if you remember, it is simply 120 f by p, right? So ns will be 120, f is 50 divided by p, it is a 4-pole machine, right? So it will be 13 to 5 50, so it is 1500 rpm. So ns is 1500 rpm and nr is 750 rpm, so it will be 750 rpm. Okay. Case 2. Case 2 is if both rotor and stator magnetic field rotate in the opposite direction. If they rotate in the opposite direction, then the n relative will be, so okay, I forgot to write down the frequency because they had asked the frequency. So what is the frequency of the induced EMF in the rotor terminals? F2 will be P by 120 into n relative. So P is 4, 120 into n relative. So it is basically 750. So it is 4 by 30. 30 is 150. Not 150, sorry. 30. 30, 3 cancel out, 25. So it will be 25 hertz. Okay. Now, case 2. If they rotate in the opposite direction. If they rotate in the opposite direction, then my n relative will be ns plus nr. So ns is basically 1500, nr is 750. This will be 2250 rpm. Okay, so this is what n relative is. So from here you can directly find out what is your frequency f2 across the rotor terminals. It will be again p by 120 into n relative. So 4 divided by 120 into n relative 2250. So if I do this right, it is like basically 1 by 3 into 225. So it will be 75. So 75 hertz. So you are observing what difference it makes. So the frequency at which the rotor cuts, sorry, the stator magnetic field cuts the rotor is much higher. Okay. So now we will understand about other cases. What if I do the opposite? What if now what we will do is I will do the opposite. What is the opposite thing? That I will connect rotor with 3-phase balance supply and I will short circuit the stator. What will happen? What will happen? So in this case, will there be any torque production? Will there be any torque production? Right? So what will happen is that I told you one thing, right? What did I tell you? So whenever this condition was happening, whenever I was giving some 3-phase supply, right, and they're short circuited, I told you two things. There was a torque developed that will move the rotor. Also, every force has an equal and opposite reaction. So that same torque will have an opposite reaction on the stator. But as the stator is fixed, it will not move. Hence, it did not move. But still, this torque was applied. So same thing is happening. Same thing will happen. What will happen is that we will use the Newton's third law. Newton's third law. What does Newton's third law say? So basically, if I am applying a 3-phase balance supply in a rotor, it is a 3-phase winding star connected. So which will generate a frequency, which will generate a rotating magnetic field, same, right? Same like stator. It will generate a rotating magnetic field which will with synchronous speed with respect to the rotor. It will revolve with a synchronous speed with respect to the rotor. Correct? It will revolve with synchronous speed with respect to the rotor. The rotor magnetic field cuts the stator conductors because they are now shorted. So thereby EMF will be induced and then current will flow. Due to the short circuit part, the currents will flow. Okay. So this induced current produces a magnetic field that opposes the cause, which in this case is the relative motion between the rotor field and the stator. So to reduce this, right, what will happen? The rotor also starts rotating in the opposite direction. Why it will rotate in the opposite direction? Like same thing, right? As I mentioned, due to Newton's third law. So of course, both the, let's say initially this was the stator rotor magnetic field. Correct? This was the rotor magnetic field. Remember, this time, what is the speed of the rotor magnetic field? Speed of the rotor magnetic field will be ns, because here the frequency is fixed, right? F, that is why. This is what? This is the speed of rotor magnetic field with respect to the rotor itself. Okay, and remember, rotor this time will move, so things will change a bit here. Okay, please keep this in mind. So this is fixed, this cannot change, it is fixed because the frequency is this time is fixed. What can change? The frequency in the stator, that can change. So this is fixed. Okay, I told you it will apply a torque in the same direction as the rotating magnetic field. If the rotating magnetic field is rotating in the clockwise direction, the stator magnetic field also will move in the clockwise direction, alignment torque will be there. So stator also, like rotor, will, this magnetic field will provide a torque to the stator, but as stator is fixed, right, it will not move in the clockwise direction, but every force has an equal and opposite reaction. So this will get a opposite reaction, rotor will receive a torque in the opposite direction of the rotating magnetic field. That's why it rotates in the opposite to its own magnetic field. The rotor starts rotating in opposite direction to its own magnetic field. Why? To reduce the relative speed between the rotor and the stator. How can it reduce? Basically, it reduces the relative speed of the rotor magnetic field, because if the rotor, this is fixed, NBR is fixed, that is ns, right? This is what? This is the relative speed of rotor with respect to the relative speed of the rotor magnetic field with respect to the rotor itself. So this is equals to what? This is absolute speed of the rotor magnetic field, absolute of the rotor magnetic field with respect to a stationary observer minus the speed of rotor. So if I want to find out the n absolute, right, n absolute of the rotor magnetic field, what is it equals to? It is equals to ns plus nr, right? And what we have to do? So initially rotor did not have any currents, right? So current in the rotor was 0, so flux was 0, so ns also was 0, because there was no flux changing, so there was no rotating field, so ns is 0, right? Initially no rotating field. But as soon as I applied a 3-phase supply, ns became active. Now this is the absolute speed of the rotating field. What is the speed of the stator magnetic field? Speed of the stator magnetic field is 0, because of course there is nothing, right? It is 0. So I want to make it 0, near 0, because initially this was 0. So initially, same thing, initially the speed of absolute rotating magnetic field with respect to a stationary object is 0. So I want to get to this value. If I want to get to this value, basically what I have to do, ns is fixed, right? I cannot change ns because the supply is fixed, frequency is fixed. I have to change nr. So what I have to do, I have to reduce this whole thing, I have to make it 0. So I have to make nr negative. So that's why the rotor rotates in opposite direction, to its own field. So I hope now it is clear. You go check any other notes, nowhere they will explain you this. Go and check anywhere else, any coaching, any other notes, right? No one will explain you this like what I have explained. Okay, own rotating magnetic field. Okay, so that's why it will be negative. Now what is the relative speed the relative speed this time, remember, it is actually, here it is ns plus nr, but nr itself is a negative number. Nr itself is a negative number. If I want to write, so what will be the frequency in the stator? Now I want to know what is the frequency in the stator. So the frequency in the stator, because like there will be a bit of confusion here. How do I write the frequency and stuff? So I will assume frequency of the stator, right, induced EMF, because still there will be some flux cut because rotor is rotating. It will be basically frequency, the relative speed is this only. Sorry, this is the absolute speed of the rotating, this is the absolute speed of the rotor field. Now what is the speed of the rotating magnetic field for the stator? That is basically depends on how fast it cuts, right? How fast it cuts. So here, right, the frequency of the stator will basically be the relative speed between the stator magnetic field and the rotor, right? Sorry, the relative speed between the rotor magnetic field and the stator winding, right? Because stator winding is stationary. What is the relative speed of the rotor? What is the speed of the rotor magnetic field? That is what we want to know. What is the speed of the rotor magnetic field? So basically, what is the F stator? How do I find out the F stator? It will be again P by 120 into N relative. Now what is the N relative this time? This time rotor is moving, right? So it will be the N relative will be the relative speed between the rotor magnetic field, whatever is the speed of the rotor magnetic field, and stator winding, right? So this time, remember, I have written here NR has to be negative, so NR cannot be positive. So I have assumed my clockwise to be the positive direction. So NR I have assumed it to be clockwise, right? But actually NR is negative. So to simplify the things, what we do, we write basically, because nth of the stator, right, it is 0 because stator winding will not move, it is stationary, right? It is 0. So basically it is the speed of the rotor magnetic field. What is the speed of the rotor magnetic field? The speed of the rotor magnetic field in absolute values is ns plus nr, but remember nr is negative. Nr is negative. Okay, so to simplify this, I know there will be confusion. As I know nr is negative, I will write the frequency of the stator winding of the induced EMF. It will be 120, sorry, P by 120 into ns will be there. It is a positive number. It is basically in the direction of the rotating magnetic field minus magnitude of nr, because there will be a bit of confusion. Because nr actually the rotor is rotating in the opposite direction, right? That's why it is minus of nr. That's why I have taken a magnitude of nr. So it is basically equals to what? Ns minus magnitude of nr. If I assume nr to be in the same reference direction, ns minus nr is what? Ns minus nr. If you remember, ns minus nr is just s into ns. Right? This we had derived because s is equals to ns minus nr divided by ns. So it is basically P by 120 into s into ns. So it is basically equals to, what is P into ns by 120? It is this value, right? P into s divided by 120. Okay, I have not written over here. It is basically, what is my f? F will be what? P divided by 120 ns, because that is how we find out the ns, right? Ns is basically the synchronous speed in which wire I am applying the three-phase supply. So this is basically ns into P divided by 120 will be basically f, right? It will be s into f. Okay, it will be s into f. It will be s into f. This will be the answer. Okay, so it is same, almost same like if I am applying a three-phase supply in the stator, same, right? Same as case 1. Okay, just here the where I am providing the supply is different, that is the difference only. Okay, so I hope you have understood this point. Okay, so yeah, this was the case for this particular thing. Now can you tell me the speed of the rotating magnetic field with respect to the stator? What is the speed of the rotating magnetic field with respect to the stator? So remember, the speed of the rotating magnetic field with respect to the stator will be this, right? Speed of rotating magnetic field with respect to stator I want to find out. So that is basically the absolute value, right? So actually I should not have written here nr because I have assumed nr to be in the same direction as the magnetic field. That's why nr is negative. If I say nr is positive, if I want to say here that nr is a positive number, how will I say nr is a positive number? How will I will change this equation to this, right? This I will just do what I will do ns minus of nr. So that will make it positive, right? If I want to say nr is a positive number, okay, how will I write it? I will write ns minus nr. So then this equation will be changed. Same thing I have done here, right? I have written the magnitude over here. So same thing I will do. The speed of the rotating magnetic field with respect to stator, basically it is asking the absolute speed because stator itself is not rotating. So it will be ns minus nr simply, right? That is equals to s into ns. So if you observe, what is the speed of the rotating magnetic field, rotating rotor magnetic field with respect to stator, and what is the speed of the rotating stator magnetic field? Okay, speed of the stator magnetic field with respect to the stator, it will basically be equals to same, right? Because it depends on the frequency of the stator. What is the frequency of the stator? It is s into f. S into f. So s into f is what? S into ns basically, right? F is ns. F is proportional to ns, right? F is proportional to ns, right? So if you see, again the same thing is happening. Although this time the speeds are quite different, right? Speeds of the magnetic fields, absolute speeds are different, but again the most important factor here is the relative speed between the rotor magnetic field and the stator magnetic field is 0. Okay, so yeah, now let's come to the third possibility. This was the second possibility. Now let's come to the third possibility. In the third possibility, what we do, we actually, if we apply both the stator and the rotor with three-phase balance current with different frequency, if I supply different frequency f1 and f2, okay, so the stator will have its own rotating magnetic field 120 f1 by p, the rotor will have its own rotating magnetic field 120 f2 by p, okay. But again, for it to be stable, right, what needs to happen for it to be stable? The relative speed between the rotor magnetic field and the stator magnetic field must be 0. Okay, so again there are two sub cases in this case, because I told you, right, the direction of rotation of magnetic field direction of rotation of magnetic field depends on the phase sequence, right? Phase sequence. So basically why? Because windings are placed, right, like this. Let's say this here a dash winding is placed in the space, b dash winding is placed, then c dash winding is placed. Okay, that's how we are placing the windings. Okay, so now if windings are placed like this, if my phase sequence is ABC, so first the peak of A will come, then B will come, then C will come. So the magnetic field will rotate in the clockwise direction. If the phase sequence is ACB, then the magnetic field rotate in the anti-clockwise direction. Why? Because we follow the peak, right? So the peak of A will come, then peak of C will come, then peak of B. So magnetic field will rotate in the clockwise direction. So there can be two cases here. If in the case 1, the basically the phase sequence is same for both the stator and the rotor. So whatever phase sequence is there for the stator windings, same phase sequence is followed for the rotor windings. So it has a sub case over here. So case A, right, out of this case 3, case A is what? If phase sequence is same for both rotor windings, rotor and stator windings. Okay, if both phase sequences are same, then one thing I know for sure, then the stator magnetic field will rotate in this. Let's assume that the reference direction is clockwise. So stator magnetic field will rotate with ns1 speed, ns1 in the clockwise direction, and my rotor magnetic field also will rotate in the same direction, ns2. Okay, now for what needs to happen, basically the thing that needs to happen is that this is the ns2. So what is ns2 and ns1? So remember, ns1 is the synchronous speed of stator magnetic field of the stator with respect to the stator, and as stator is stationary, then there is no problem. But what is ns2? ns2 is the synchronous speed or the speed of the rotating magnetic field of rotor magnetic field with respect to the rotor. So rotor itself can also rotate. So what is the absolute speed of rotor magnetic field? So I will write another quantity, n r, n absolute of rotor magnetic field. It will be equals to basically the speed of the rotor plus, if I assume the rotor is also rotating in the same direction, I will say why it will rotate in the same direction, nr plus ns2, right? Because ns2 is the speed with respect to the rotor. So this is the absolute speed, right? So now what I need to find out, I need to say one thing I know: for alignment force to work, for torque production to work, what do I know? The relative speed between the rotor magnetic field and stator magnetic field must be 0. So basically what they're telling me, what is the stator magnetic field? Speed of the stator magnetic field, ns1. What is the speed of the absolute speed of the rotor magnetic field? This ns1 is respect to a stationary object. So I should write the absolute speed because both of them should be with respect to a common point. So common point is a stationary object. So it is nr plus ns2. So minus of nr plus ns2. This must be equals to 0. So from here I get this equation that the rotor must rotate to make the relative speed 0, and R will be equals to ns1 minus ns2. Okay, from here we get the equation of the case 1. Now in the case 2, if I say in the case 2 what will happen, if the phase sequence is 0, if the phase sequence is opposite. So if the phase sequence is opposite, that means if the phase sequence is opposite, then basically if the stator magnetic field is ns1, then the rotor magnetic field will be in the opposite direction, it will be ns2. Now how will I reduce the relative speed? So the rotor itself has to rotate in this direction to compensate this value, right? To compensate this value. So basically what should be the rotor speed? Like I can intuitively say rotor speed will be, first of all, it has to cancel out this ns2, right? Why? Because the relative speed between the stator magnetic field and the rotor magnetic field must be 0. So first of all I have to take this one out. So it will be ns2. Now it seems like to a observer, stationary observer, the rotor magnetic field is 0 speed. If I am rotating the NR in the opposite direction, it feels that the rotor magnetic field is rotating at 0 speed, no speed, stationary. But again, the relative speed between the stator magnetic field and the rotor magnetic field must be 0. But I have to move another NR1, NS1, so that I make the relative speed between them 0. So with respect to a stationary object, the rotor magnetic field should also move with the speed of ns1. The stator magnetic field also should move with the speed of ns1. Okay. So now I will prove it. I will prove it to you. Opposite. So what will happen? The relative speed. So this condition must be satisfied. Same condition, right? So this time, what do I know? That the NR is moving in the opposite direction to ns2. So if I assume my ns2 to be the reference, ns1 to be the reference direction, right? ns1 is reference. So ns1 is reference, that means it is the positive. So ns1 here is, I have written ns1 positive. So basically here, right, in this place, I have to write the absolute speed of rotor magnetic field in same direction as ns. So this will be deleted. This will be deleted. So what is the absolute speed of the rotor magnetic field? So I know ns2 is what? ns2 is the speed of the rotor magnetic field with respect to the rotor, right? So ns2 is equals to what? ns2 is the speed of the rotor magnetic field with respect to the rotor, right? So it is the so what I can say is that what is the absolute speed? Previous, if I go back in the previous one, right? How did I find the absolute speed? Absolute speed was both the rotor speed plus ns2, both were, if you remember, both were moving in the same direction. ns2 and the rotor also was moving in the same direction. That's why they were added. But this time, if you remember, rotor is moving in this direction and the ns2 is moving in this direction, opposite direction. So they will be subtracted. It's same like if a box here is moving with 5 meter per second, right? And in the same box, right, I have this particular ball. In the same box, I have this ball, okay? And this ball itself is moving on the left hand side to 1 meter per second. So how much has this ball moved forward in one second? Remember, previously, if you remember the case, previously the ball was a different object, like it was not placed in the box and the box was here, right? That's why we were subtracting it. We are finding out the relative speed. But now I am not doing it. Now the ball itself is on the box itself. Okay. So now, can you tell me how much has the ball moved in front in a second? In a 1 second. If you see, the box will move by 5 meters in a second, right? The ball, as it is on the box, it will also move by 5 meters. But remember, it also will move backwards by 1 meter on the box itself. So overall, 5 meters in front, 1 meter backwards, so overall it will move 4 meters. So that's why there is this subtraction sign, right? So I hope you have understood. So the rotor's field is here nr, so absolute speed will be what? Nr. So this is the first number, that is the nr 5 here, this speed, minus the speed in the opposite, because the speed of the rotor field is residing on the rotor itself, that's why. So it will be minus of ns2. Now I will replace this value over here, so this will come over here, so this will be nr minus ns2. So again the same equation I will apply, that the relative speed must be 0. If the relative speed is 0, that means I can say that my nr from here, from this equation I can say nr will be equals to ns1 plus ns2. Okay, so the rotor, this time the rotor speed will be ns1 plus ns2 if it is case b. So same thing, basically this time the frequency also what will be the, like, rotor speed also will increase, that is the main thing, right? If ns1 is some 1500 rpm, ns2 is some 750 rpm, in the previous case the rotor speed will decrease, I mean it will not be equals to the highest speed, here it will increase. So this is one indication to find out whether both the phase sequence are same or not. So you can identify the phase sequence of two different supplies from this test. How? So you can find out the synchronous speed with this formula, and you can observe the rotor speed. If the rotor speed is less than the highest synchronous speed, so if I take example, like let's take example, okay, let's take example that in this case example is, so this particular thing, right, I'll put it here. So basically what is this useful for? This particular arrangement, is useful if we want to check the phase sequence. If you want to check the phase sequence, this arrangement is very, very useful. How? So let's take example that ns1 is 1500 rpm, synchronous speed of the rotor will be 750 rpm. So if I apply both the supplies, right, different supplies in rotor and stator, if I observe that, so if I observe that nr is coming out to be 750 rpm, that means what? That means it is actually the case 1. That means, like, I will measure the speed, basically I will see it is roughly near to 750 rpm. That means it is basically, that means the phase sequence of rotor and stator are same. And case 2 is, let's say, if nr is coming out to be 200 and 250 rpm. How is it 250 rpm? Basically it is the sum of the two synchronous speeds. So basically it is the sum of the two synchronous speed, it is not difference. So that means it is basically the case 2, I mean this is the case A, sorry, case A and case B, right? Case A and this is the case B. In case B, basically we know the phase sequence is opposite. Rotor and stator are opposite to each other. Okay. So yeah, that's how we can do it. So whatever we had discussed, same thing is written for continuous production of torque. Rotor magnetic field must be stationary with respect to each other. There will be constant relative speed. So to ensure coupling, so this is the sub case one which we had discussed, when the basically like n relative will be this ns1 minus nr, which will be equals to 0 for the case one, where the both fields are rotating in the same direction, basically the same phase sequence, same phase sequence. So then basically your nr comes out to be ns1 minus ns2, right? From here we get the value. Okay, and for the case 2, if the fields rotate in the opposite direction, if the fields rotate in the opposite direction, that is different phase sequence, opposite phase sequence, okay, this will, I will not have enough space. I have to think about something. So okay, this side I can lock it, I can reduce the space of this. Yes, this can be reduced. This can also be locked, this can also be reduced. Yes, lock can be moved away. So this can stay, like already we have discussed. So whatever we have discussed, right, same thing is written over here. So that's why I'm not explaining it anymore. I'm just directly showing it to you. Okay, so yeah, your n relative will be this. So from here your nr comes out to be ns1 minus ns2, and here your nr, because n relative will be 0, right? N relative will always be 0. So nr will be equals to ns1, like this. Nr should be with negative sign basically, or ns2 will be sorry, the equation was this, right? Yeah, nr ns2, this should be negative basically. ns1 minus ns2. Okay, so like these are the, sorry, plus ns2. So these are the equations basically. These are the two cases. So actually question came, it's not like I'm teaching you something that is not relevant, right? It is relevant. It actually, this kind of questions do come in examination. So pause the video, try these questions out by yourself, then I will solve this question. So I will solve this question. A 4-pole induction motor supplied by a slightly unbalanced 3-phase 50 Hz source is rotating at 440 rpm. It is slightly unbalanced. Okay, the electrical frequency of the induced negative sequence current in the rotor will be. Okay, they are asking quite a interesting question. So it is slightly unbalanced. So we have not till learned what is positive, negative and zero sequence. That we will learn in power system analysis, but briefly I have explained it to you in while discussing about harmonics of transformer. Okay, so like iron guys can skip this. Okay, they don't have to worry about this. But for electrical guys, they will already be knowing, because I've already discussed about this briefly in transformers, harmonics in transformers, right? Don't worry, it will be discussed in power system as well. So whenever a supply is unbalanced, if it is a balanced supply, right? If it is a totally balanced supply, so I will have basically only a single component, that is a positive sequence component. So positive sequence component is the component which will be in the same phase as the supply. So if the supply phase is ABC, so the positive sequence component will also be ABC. But what about the negative sequence? So if it is unbalanced, right? If it is unbalanced supply, it will contain the positive sequence, of course, just like the fundamental component. Then it will contain the negative sequence component, whose phase sequence will just be opposite. That's why the name negative. So phase sequence will be opposite. So it will be ACB. And the third kind of symmetric components we have is zero sequence. Zero sequence component. Like these are all phase shifted by 120 degrees apart, but the rotation here is different. Okay, here it is different. So here they are lying in the same phase, so this will be A, B, and C. Okay, zero sequence means all of them are in the same phase. There is no phase difference between the three components, right? They're asking the frequency of in hertz of the induced negative sequence current in the rotor. Actually, this is a very good question. Okay, so they are only asking, there will be, because it is unbalanced, right? Because it is unbalanced, there will be three components. One will be the positive sequence. Due to the positive sequence in the primary, so basically, right, here I have the stator windings. So, and here I will have the rotor windings basically. Just like a transformer, just like a transformer, what can I say? What can I say? I can say that if I am applying the positive balance supply, right? Positive balance supply, here some positive EMF, like positive sequence EMF will be generated. If I am applying a negative balance supply here, right, what will be the EMF induced? It will be negative. Okay. Now what is important? They are asking me the electrical frequency in hertz of the induced negative sequence current. How will I find it out? So the important key point here to note is that I will just copy the rotor. Yeah, this one, right? I will copy, not this one actually. Yeah, this one only I copy. So if I apply a supply which is positive sequence, then of course the rotor will rotate in the, let's say if the direction of rotation of the magnetic field, stator magnetic field, is in the clockwise direction, ns, right? Then the rotor also will rotate in the same direction, nr. Okay, that is what we know, basic thing, right? That is already what we know. Now the thing here is, they are not asking me what is the EMF induced due to the balance supply. Now the supply contains harmonic, so it has both the positive sequence and negative sequence. Generally the negative sequence magnitude will be lower than the positive sequence, so overall the positive sequence will dominate. So overall the rotor will still rotate in the same direction as the magnetic field generated due to positive sequence component. Okay. Now, what can I say? So rotor also will rotate in the same direction only. So this is fixed, right? Overall assumption is the basically the positive sequence component will dominate the negative sequence component. So rotor will still rotate in the same direction, but they are asking me what is the EMF induced due to the negative sequence. So what is the direction of the negative sequence rotating magnetic field? So it is also rotating, but it is in the opposite direction to the positive sequence. So this is the NSP, that is the direction of the magnetic field of the positive sequence component. The NSN, right, will be in opposite direction, right? The speed of the rotating magnetic field of the negative sequence component. So it is in the opposite direction. So if it is in the opposite direction, now how do I find out the frequency induced due to this? So the frequency induced due to this will be what? F2 due to the negative sequence component will be what? P by 120 into the relative speed. What is the relative speed between the stator negative field component and the rotor negative field component? So if I assume this to be my reference, right, it is in the opposite direction. So it is basically what? If they are in opposite direction, it will be what? It is absolute speed of the stator magnetic field, it is NSN, right, absolute speed with respect to a stationary observer, minus the absolute speed of the rotor. What is the absolute speed? The rotor is rotating in opposite direction nr, so it will be minus of nr if I assume my anti-clockwise direction to be the reference, correct? That's why it is the relative speed, because rotor is rotating in this direction and stator magnetic field is rotating in the opposite direction, so the relative speed is more. Okay, remember this is the stator, this is not in the rotor. That's why here these are getting added, because this is in the stator, not in the rotor, in the stator. Okay, I know there will be a bit of confusion. Please think on your brain more, give more pressure to your brain, you will understand this. Okay, so this will be P by 120 into NSN plus NR. What is NSN? NSN is same as NSP, just the direction was opposite. So NSN will be 120 F by P, just the direction was opposite, direction opposite to NSP. So 120 into F is 50, I guess, right? 50 hertz and 4 pole. Okay. What is NR? NR is basically 750 RPM. NR is 1440 RPM, right? Direction is already taken into account. So basically the F2, right? F2N will be P is 4 by 120 into 1500 plus 1440. So if I find out this value, it will be 1500 plus 1440 divided by 120 into 4. So it comes out to be 6. Sorry, have I done something wrong? Sorry, just hold on. 1500 plus 1440 into 4 divided by 120. Yeah, it will be 98 hertz. This will be the answer. So this is a very elegant question because negative sequence component was there. Maybe that concept was a bit weak, so you may have struggled on that part. Okay, so this thing we have already previously discussed, that why the no load current is higher. The no load current is higher than in transformer because we are comparing with the transformer itself. It is higher because, of course, the magnetizing component of the current will be higher. Why will the magnetizing component of the current will be higher? Because to produce the same amount of flux, this NIM divided by reluctance. So as the reluctance is higher, so the magnetizing component also will be higher to produce the same amount of flux, right? That's why the no load current will be higher, because no load current is a combination of both the active component, the loss component, coal loss component, and the magnetizing component. So in transformer it is 2 to 5% of the full load current. In three-phase transformer it is 30 to 40% of the full load current. Okay, that is the difference. Okay, so that's like why is it is higher. The reason is explained over here. Okay, so yeah, as I told you, it is combination of both the magnetizing component and the coal loss component. Okay, so E1 is this value, 4144 F5 N1 KW1. E2 is the, like, this is the induced EMF per phase in the primary. Okay, what will be the induced EMF in the secondary? Can you tell me what will be the induced EMF in the secondary? So induced EMF in the secondary, right, E2, it will not always be like a transformer. It will be 4.44 into F2, because I don't know, the frequency might change at which, at the rate at which the flux is cutting, right? F2 into 5 will be same, because same flux is linking the primary and secondary. Number of turns into the winding factor, it is just a factor. How am I placing the windings? So remember, in case of transformer, for a transformer, your F2 is F, but for an induction machine, your F2 is SF, right? So it makes a difference in the equivalent circuit. So it is, if S is 1, then the circuit of the equivalent circuit of the induction motor and transformer will be same. But if S is not 1, S is less than 1, then they are not same, because they are not in the same frequency, right? So we will discuss about the equivalent circuit. So like these are additional factors in an induction motor that is different than transformers. So it has rotating magnetic field which has losses. Even at no load, the stator creates a rotating magnetic field which incurs iron loss and steel loss. Because magnetic field is rotating, it will have losses. Friction and windage, unlike transformers, there is no moving parts, so there is no possibility of friction and windage loss. Now let's read the third point. Actually, the third point is not correct here, right? They are talking, no, okay, we will ignore this point, because we are not discussing about the rotor induced current, because it is open circuit. Even if rotor is open circuit, then also there will be high no load current due to these particular factors, right? Of course, my IM will be higher. So if IM is higher, I have to build up the same amount of flux, because the reluctance is higher, so I have to provide the increased current. And friction and windage loss are there, because now there are rotating loss. Even though the rotor is not rotating, even if the rotor is slightly rotating, it has to overcome the friction and windage loss, right? So if this like phone is rotating, it has to overcome the air, right? And there are mechanical parts. So previously in transformer, those kind of things were not there. So these are the reasons why no load current in induction motors is higher compared to the no load current in transformers. Okay, these are the main reasons. Okay, so now let's briefly discuss about the equivalent circuit of a induction machine. What is the equivalent circuit of an induction machine? So if I take the case of a standstill case, if I take the consider, or let's consider the general case. So in a general case, do you remember what was the circuit of a transformer? So that circuit of a transformer, if I remember properly, I had a winding resistance R1, I had a leakage reactance L1, I had a magnetizing reactance LM, let's say the mutual inductance. Basically, this is the reactance of the air gap now, not reactance, sorry, inductance of the air gap through which the flux passes, common medium. Then what else do I have? Then I have the secondary winding resistance. This is the stator resistance, so I can write this as SRS LLS. Okay, now I can write here the secondary rotor resistance, so this will be RR, right? Rotor winding resistance. And rotor winding also will have its own leakage reactance that will not link the rotor and the stator. Of course, every winding will have. So here I will have a, so I will draw this in a different color actually. So this will be the flux of the stator that will not link the rotor, and here I will have a leakage reactance of the rotor that will not link the stator. This is the fire. Okay, and of course if it is in running condition, like I'm drawing the single phase, okay, per phase I'm drawing the per phase equivalent. Of course for three phase, three other phases will be there. I'm just drawing per phase equivalent, so it is the per phase equivalent, that is what I'm drawing. So in per phase equivalent I give some phase voltage here, V phase, okay, with respect to neutral, and in the secondary I will have this winding, and the basically rotor windings will be short circuited to the neutral, correct? It will be short circuited, right? There will be short circuit in the rotor for the currents to flow. So the important factor to understand here is, remember, the frequencies are not same, so I cannot directly connect these things. I cannot refer here, right? I cannot refer to the left hand side, because remember the frequency is not same. Here the frequency is f, right? It is V phase and f. What is the frequency here? The frequency here is the secondary induced rotor induced EMF, comma, frequency is Fr, the rotor frequency. What is Fr? Fr, the rotor induced EMF frequency, is S into Fs, or F, right? S into F basically. So they are not simply same. So I cannot actually bring this to the left, I mean connect these two together and refer it to the stator side as we used to do it, in the transformer. Is there any solution for that? Is there any solution? So solution is there, that I will discuss obviously. So of course there is this, don't forget there is this what do you say, core resistance as well, right? There is this core resistance as well, okay? So the thing is, let me write few KVLs and KCLs, then we will discuss about all things, okay? So basically this, right, is not E to R, or I can write it as E to S, the induced EMF in the secondary. So what is V phase equals to? If I write the KVL, there are two loops, right? This is the, like here I will have an induced EMF in the primary. This will be the induced EMF of the primary or of the stator, correct? This will be E1 and this will be the E to S, okay? So let me write few KVLs here. So this is the loop 1, let's assume this is loop 1, and if I write the KVL here, what is the KVL? KVL is basically E to S, the induced EMF will be equals to the drop. Let me write the current here, that is rotor current, right? IR. You can write it as I2 as well, that is also fine, whatever you want to write. I will write IR. So it is RR into IR vector plus j omega LR. This is the reactance of the leakage reactance of the secondary into the current IR, right? Okay. Now what is the basically E to S equals to? What is E to S equals to? So we derived a equation, right? If you remember, what is the induced EMF equals to? Induced EMF E1, right, is equals to 4.44 or root 2 into pi into F into phi into n1, correct, right? What is E2 equals to? E2 is equals to root 2 into f into s into f, because rotor frequency is different, right, into phi because it's the same flux, both flux links the stator and the rotor, into n2. Now for a second, if I assume, uh, okay, don't have to assume anything. So what will I be able to write down? What will I be able to write down? So I will be able to write down what is my E2 by E1. So E2 by E1 is basically S into N2 divided by N1. So I cannot simply, previously, right, in transformers, this S term was not there. So I did not simply refer it, right, on the primary. How can I refer it now? So basically, if I want to connect these 2 points here, right, if I want to connect these 2 points here, how can I connect it? So the E2 actually is equals to S into N1, N2 divided by N1 into E1. Okay, so that is what my E2 is equals to. Got it? Now, what we actually do, I have to make this, like I have to connect this. Can I simply connect it? Can I simply connect it over here? So how will you connect it over here, right? So one thing I know, what is my IR? IR is basically E2S divided by RR plus X JXR, right? Because it is simply short circuited. Now what is XR actually? XR is basically 2 pi f, not 2 pi f, 2 pi SF, because the frequency on the rotor is S into F into LR. So IR is basically equals to E2S. E2S, I know what is the value of E2S in terms of E1. So it is S into N2 divided by N1 into E1 divided by RR plus JXR. Okay, this is what my E2S is equals to. I just derived it here, right, just here. So let me write the vector. So this is equals to E1 bar divided by, if I divide by this value, right, it will be RR divided by S into N1 divided by N2 plus J. Remember, I'm dividing by S, right? If I'm dividing by S, already there is, like, if I assume this is my XR at S. XRS is basically a fixed value, that is 2 pi f LR, right, where my slip is 1. That means the rotor frequency and the stator frequency is same. So then it comes out to be XRS, right, because I'm dividing by S, the S is getting cancelled, right? N1 by N2 is there already, that is also obviously there. So into N1 by N2 will be there. Okay. One more thing, this is rotor current in the rotor itself, but I want to write down the, like, basically I want to convert this circuit, take this circuit to the primary. So one more relationship we have to use that MMF balance equation. So what is the MMF balance? I know N1 into the stator current, right, whatever induced stator current, like, sorry, basically the rotor current is flowing in the rotor itself, which will induce a MMF. To cancel out that MMF, I am writing N1 into IR dash. This IR dash is just the referred current from the rotor to the stator side. That's it. Okay, same equation as we used for the transformers. So this will be N1 into IR dash will be equals to N2 into IR, right? So from here I can get this next relationship, that IR bar is equals to N1 divided by N2 into IR dash. So I can write here N1 into N2 into IR dash equals to, basically, right, I want to connect these 2 points here. So basically if I want to connect these 2 points here, some IR dash current is going. So that is what I am trying to write over here. So basically ultimately I am trying to write what impedance will come here. Basically I want to find out the value of E1 divided by IR dash, because here if you see, here if you observe, that I have E1 here and I have IR dash. So that will, if I find out the ratio between these two, that will be the equivalent impedance. So this will go on the left hand side. So basically N1 by N2 will be multiplied. So this will be RR divided by S into N1 divided by N2 whole square plus this J into N1 divided by N2 whole square into XR dash. Okay. So from here I can actually draw the equivalent purpose circuit. So basically all this will be present on the left hand side. On the right hand side, a resistance whose value is actually not just RR into N1 divided by N2 whole square. It is basically RR divided by S. This S has a significance. We will discuss about that. So how can I connect it? Because remember, the as I'm dividing by S, right? As I'm dividing by S, the frequency is same. Frequency became same. Okay. Luckily, the frequency is same. Frequency became same for the inductive part, right? Because what is frequency dependent here? Only the inductance. The resistance is not frequency dependent. So frequency became same luckily. That's why I'm able to connect it here, right? If the frequency is not same, I will not be able to connect it here. Okay. So this will be, I will get a resistance whose value will be RR divided by S, right? RR dash divided by S, because what is RR dash? RR dash is the referred to the primary, referred resistance of rotor to the stator. So it is basically RR into N1 divided by N2 into whole square. Whole square. Okay, so it is RR dash divided by S, and I have inductance, that is XR dash, XRS dash, because it is the standstill. Like here slip is 1. If slip is 1, that means the rotor is not moving at all. It is standstill if slip is 1. Okay, and then of course the rotor circuit, it is short circuited, so nothing will be there, it will be short circuited. So this is the equivalent per phase circuit. Okay, now we make few changes. About those changes we will discuss about that, but for now I hope you have understood that some rotor current IR dash will flow due to the induced EMF, that is RR dash divided by S and XR dash. So this, right, is not RR dash only, it is divided by S, because I have to factor in the slip, because slip is also present over in the circuit. Okay, so yeah, same thing basically. Like here I want to explain basically the air gap flux, the leakage flux of the stator and the leakage flux of the rotor. So what is the air gap flux? Air gap flux is the flux that will link both the rotor and the stator. So basically the air gap flux, it will start from the north, it will connect this south pole, and here also it will start from the north, it will connect the south pole. So the air gap flux will be somewhat like this. This will be the air gap flux, and this will be the rotor flux. Okay, so okay, sorry, right, I'm making a mistake. Basically the flux will link something like this. It will come from here, it will divide in the south pole, then again internally it will go here and it will link here, right? Here also the same thing. So basically the flux will flow through the air gap, right? So cannot like this, it will go like this and rotate in the clockwise direction. Yeah. What about the leakage flux? So leakage flux, right, only will connect both the stator and the only the stator. So basically it will avoid the rotor. So it will start from the north pole, it will move, go to the south pole and come back. It has to be a closed loop. Again from here as well, it will avoid the rotor. It will just connect, link with the stator only. Okay, same here again, same basically. Okay, where did I go? Okay. Same here, that here also for leakage flux of the rotor, it will just avoid the stator, it will only link with the rotor itself, right? Okay, so these are the leakage flux basically of each of them, leakage flux and the magnetizing flux. I hope that that difference is clear, and this is the equivalent circuit, okay, that I was discussing about. Now one important fact to note here is that what is the losses? What are the losses? How do I find out the losses? So I know what is the iron loss, Pi, overall iron loss, right? What is the voltage across this element? E1 divided by Ri. So that will give me the iron loss. So it will be basically E1 whole square divided by Ri. Okay, that is what the total losses are. Now what else can I find out? So these losses will include what? Iron losses will include what? Iron losses again will include this time both the hysteresis loss. What does hysteresis loss depend on? It depends on basically Steeman's constant, right? So basically if you remember, your hysteresis loss pH is frequency dependent and flux density dependent. So it is Bm raised to power x and frequency dependent. Frequency of what? Frequency of the stator. Okay, frequency of the stator, because I have converted this circuit, inductance is also in the stator winding only. Okay, and what is the other loss? Other loss is the eddy current loss. What is eddy current loss? Eddy current loss is Pe is proportional to Bm whole square this time and F square. Okay, that is what my eddy current loss is proportional to, right? So these will be basically the losses. I hope you have understood this basic point. Okay, and things are written over here. So per phase equivalent, so there will be air gap magnetizing flux, so which is responsible for the magnetic induction. It rotates synchronously with stator field and maintains the coupling. So why is this frequency f? If you remember the air gap flux, right, why is the hysteresis loss dependent on frequency f and not sf? Because air gap flux rotates what? With synchronous speed. And rotor flux also rotates with synchronous speed with respect to a stationary observer. So that's why we will use the frequency f only. We will not use anything else. We will use the frequency f only. Okay, so I hope that part is clear. Okay, leakage flux already we have discussed, that will not link both the stator and the rotor. It will link only either the stator or the rotor. Okay, so stator side I will have a resistance R1, which is the per phase. Remember we are drawing the per phase because Transformer, initially when we started to draw the equivalent circuit, it is only a single phase transformer. Now we have 3-phase winding, right? So that's why whatever parameters I will write, those all will be per phase quantities. So here, right, whatever R1, LL1, whatever these values are, these are all per phase quantities. Okay. So R1 is per phase resistance of stator winding. R1 is per phase resistance of stator winding. X1 is 2 pi FL1 per phase leakage reactance of the stator winding of the stator due to leakage flux. Okay. So X1 is 2 pi FL1 per phase leakage reactance of the stator due to leakage reactance. Right. Magnetizing branch across air gap. So Xm is equals to 2 pi LFN. Magnetizing reactance representing the magnetizing inductance required to set up the rotating magnetic field in the air gap. Okay, this is the magnetizing reactance that is responsible for setting up the air gap flux. So on the rotor side, okay, if I refer it on the primary, R2 dash is the rotor resistance referred to the stator. Okay, that is what is written over here. If I show you this circuit, R2 dash or RR dash, both are the same only. Just I hope you understand the point, right? R1 is stator, R2 is rotor. Okay, so R2 dash is the referred one. So what is my R2 dash equals to? So what is my R2 dash actually equals to? R2 dash is equals to N1 divided by N2 number of turns whole square into R2, right? Same formula as that transformer. And remember, X2 dash is not just the rotor leakage reactance. X2 dash is the standstill leakage reactance, because what happens in standstill? Slip is 1. If slip is 1, then that becomes my X2 dash. Okay, because it is independent of S. It is independent of S. Okay, that's why. Please remember. So X2 dash is not just the rotor leakage reactance. It is the standstill rotor leakage reactance. Okay. It is the standstill rotor leakage reactance. I hope you have understood this point. Okay. So X2 dash is actually equals to 2 pi F into L L2 into N1 divided by N2 whole square. Okay. Actually, if I see on the secondary side, my X2, the actual value of X2 is 2 pi SFLL2. But as I'm making slip to be equals to 1, that's why it is the standstill rotor reactance. Okay, so that I can, like, it is frequency independent, so that I can connect the two circuits together. Okay, otherwise frequencies will be different and I will not be able to connect the two circuits. So the same thing is written over here. At standstill, this becomes this. This is the E2 induced EMF frequency. During operation, this happens. Z2 becomes this. Okay, we find out the values, and yeah, from there so one more thing is that the induction motor is actually a lagging load. Overall, it is a lagging load. Why? Because it has a leakage reactance here and it has a resistance. It does not have any leading component. So one more thing I can conclude, that induction motor is a lagging load. Okay, that is the conclusion that I want to take away. Okay, so I hope most things here are clear. Now, like we have already discussed how to write the rotor equivalent circuit. If I want to interconnect the rotor equivalent circuit, how will I interconnect? So you can see one thing, right? What is the circuit that I have drawn? Okay, if I want to interconnect these things, right? So let me copy this one. So if I want to interconnect these from this to a single circuit, because only then we will be able to analyze, right? We will be able to apply KVL, KCL. I will not be able to analyze the circuit like this, right? I have to convert this. So what I do, I make it frequency. I kind of want to make it frequency independent. So how will I make it frequency independent? I want to connect these two, right? Okay, and it basically it is there is no currently there is no load connected, it is short circuited. Okay, short circuited, it is R2 dash divided by S, it is X2 dash only, X2 dash S, it is the standstill reactance. Now remember, if I connect a load, what will happen? If I connect a load, the slip will change. We'll see this, right? Let's say this device, right, is simply rotating. No load is connected. As soon as I will connect a load here, this will rotate with a slow speed. Same like your fan, right? Just take example of your fan. If you see, the fan is rotating, right? Now, after 3-4 years, again, if the dust is there, in the same level of the regulator, the fan will not rotate in the same speed because there is more load. So that's why the speed has slowed down. Same like you, right? You are trying to push a particular object, and opposing force is there. Of course, you will not be able to push it the same amount, right? So same thing is here. As soon as I will connect a load, the slip, right, the NR will go down. The rotor speed will go down as soon as I will connect a load. Why NR will go down? What is the torque equation? So if let's say it is no load, still there will be some friction and windage loss, all those things will be there. So there will be some load torque. Okay, and that will be equated with the developed electromagnetic torque, due to which the speed is constant, that is NR. Now as soon as I will connect a load, the load torque will increase, right, to TL dash. So TL dash will increase, right, load torque will increase. So if TL dash is increased, what is the torque equation? Torque equation is TE minus TL, right? So TL has become TL dash, so TE minus TL dash is now negative because previously TE was equals to TL. Now the load torque has increased, so it is negative. So it is what? Negative torque. It is opposing torque. So it is deacceleration. Deacceleration. So basically what is happening? The speed will reduce because it is deacceleration. The rotor speed will reduce. If rotor speed reduces, what is the slip formula? Slip formula is Ns minus Nr divided by Ns. So if rotor speed reduces, what happens? This whole thing will increase. So slip will increase basically. Slip will increase. So if slip increases, basically what happens? This resistance will increase. Sorry, yes, this resistance will not increase. Sorry, this resistance will reduce. This resistance overall will reduce. Okay. So basically, the problem is this quantity, right? I am not comfortable with this quantity. It is just like a variable resistance, right? It is just like a variable resistance. Basically, as slip is varying, so the resistance also is varying. Now, I am not comfortable with this. I am not comfortable with this. It is not showing the correct thing, right? If slip is increasing here, what is happening? It is showing that resistance is decreasing. That means kind of it is telling me that the load has reduced, right? Because if what do you understand by electrical load? By electrical load, we understand a resistance, right? If I am saying increase the load, that means you say that the R2 has increased. Kind of that only. Kind of that. Okay. Something like that. If I say load has increased, right? So actually, what I want to do, I want to write this thing in a different manner, so that I want to show this that how my load is varying. So actually in transformer, what used to happen, if you remember correctly, in case of transformer, this was supposed to be R2 dash, right? This was R2 dash and this is supposed to be X2 dash, correct? And here I had a load connected. Let's write here RL, okay? Now can I equivalently convert to this circuit? And my load is varying. This will be a better approach. Okay. So what I will do, I'll copy this circuit, because I don't want to vary the winding resistance, because like winding resistance here it is mentioning that winding resistance is changing. Actually no, winding resistance is not changing. I'm just changing the load. So the load resistance is changing, right? Not the winding resistance. So what I can write over here is I can convert this circuit into this one to better understand. Like physically, actually the circuit is this only, but we can do anything we want. In a circuit, we can do anything we want, right? So we will do anything we want, okay? We will do anything we want. So can I equivalently write this? How can I write it? So I know what is the equivalent resistance seen from here, because the reactance is not changing, only the resistance is changing. What is the equivalent resistance here? So the equivalent resistance here, if you see, it is R2 dash divided by S. What is the equivalent resistance on the second circuit? It is R2 dash plus RL. So from here, can you find out what is the value of RL? RL equals to R2 dash by S minus R2 dash, okay? So this will be R2 dash divided by 1 by S minus R2 minus 1, okay? So basically I am converting my circuit to further simplify it, right? That will be a better way to approach it. So one more thing is, in reality, like actually my rotor circuit, if I am converting here, it is becoming frequency independent, this inductance, right? In reality, it is not. This inductance is actually changing. It is not frequency independent. So this reactance is actually changing. It is not frequency independent. So we will write down two versions, right? We will write down two circuits of the rotor. So before this, right, we want to discuss about rotor circuit, rotor only. It is not a single like equivalent circuit. I want to discuss about rotor circuit. So there are two configurations of rotor circuit. This is the first one. Where did it go? So if I copy this, right, this is the first one basically. And this is the second one, okay? So in case of second one, this is basically like my equivalent resistance is R2 divided by S, as we had, like if you remember, if I am referring to the stator, it becomes R2 divided by S, and my reactance becomes Sx2S, which is standstill. It is basically 2 pi F into LL2. In this case, the reactance here, right, is X2. What is X2? X2 is 2 pi SF into LL2. So basically, this is the actual physical circuit, right? Actually what is present in the rotor, actual physical circuit. And this is some equivalent circuit that I am writing, okay? Equivalent circuit. So what is this equals to actually? Like this one, right? What is this equals to? This is simply equals to S into X2 S, okay? So this is the equivalent circuit, okay? Now you might have a doubt, sir, why we use this circuit, why not use this? First of all, we are using this because it becomes frequency independent. Here it is X2 dash, so I can simply connect it to the stator side, okay, for our own analysis, okay? But in reality, this is the circuit. But what is different between this one and this one? If I want to understand what is the difference, so if I see what is the power consumed in the first circuit and what is the power consumed in the second circuit, right? In the first circuit, the power consumed right, is simply equals to because it is per phase power. I am discussing about per phase, everything is per phase here. It is I2 whole square into R2. Okay, and what is I2 equals to? So I2, what is I2 equals to? So here, right, it is E2S, here also it is E2S, but here the frequency is F simply. Okay, so what is I2 equals to? So I2 is equals to simply, in the first, I'm talking about the first circuit, it is E2S divided by, I'm talking about the magnitude, under root R2 whole square plus, this is simply S into x2S whole square. And from here I can directly say what will be the power in case in the rotor side. It will be E2S whole square divided by R2 square plus S x2S whole square into R2, right? In the second case, what is the power consumed? I want to write down in the second case what is the power consumed. This is the case 1. Okay, case 1. In the second case, right, power consumed, it will be what? The I2 current will be what? I2 will be E2S same induced voltage divided by, this time the equivalent impedance has changed. It is R2 divided by S whole square, this will be whole square, plus this time it is not Sx2 anymore, it is simply x2S whole square into R2. So if I want to like write this in terms of this, right, just I have just written the equivalent impedance here, you can see. Okay, x2S is the standstill rotor reactance. So now if I want to compare these two, I have to multiply by S square on both sides, right? If I want to compare these two equations, I have to multiply by S square on, okay, sorry, the resistance also has changed, right? It is R2 divided by S. Remember, like what is this equals to? Basically here, right, in the second case, it is magnitude of I2 dash, okay, I'm just talking about the second case, into the resistance in this case is R2 divided by S. It is R2 divided by S. So here it is R2 divided by S. So basically the power in the second case, right, power across the rotor in the second case is equals to, if I multiply by S square on both sides, it will be E2S whole square x2 whole square, and 1s is getting cancelled. This is R2 whole divided by 1 by S. So if I notice one thing, that in the second case, what is happening? Second case, the like PR, basically it is what? This whole thing is PR1 only. This whole thing is PR1 only if I compare, right? So just this one is divided by S. So PR2 is basically equals to PR1 divided by S. So some mismanipulation is happening. Okay, something wrong is happening. If I just simply use the rotor resistance to be R2 by S, there is mistake in the, like what is this? This power is the, like this, whatever loss this is the mechanical power that I'm receiving at the output, right? Including the winding losses as well. So this, right, whatever power input I'm giving here, this power consumed is equals to what? This power is combination of both the mechanical output power that I will receive, mechanical output power, this we will discuss in the next lecture, plus the rotor copper losses, right? It is a combination of both, right? It is a combination of both. But the problem is here, right? It is showing it is PR1 divided by S. So it is something is wrong. Something is wrong. So we want to separate out the rotor copper losses and the mechanical output power. So I should have actually done this first, then I should have drawn it. Okay, that's my mistake. So that's why we changed this circuit to this R2 dash by S. Instead of this, we went to this format. So actually, this is the load here, right? This is the load actually. I mean referred. But we want to separate out the things. We want to separate out what is the rotor copper loss. Rotor copper loss will be, in this case, it will be I2S into R2 dash, I2S whole square into R2 dash. This is the rotor copper loss. What is the mechanical output power? Mechanical output power will be simply this value, right? Mechanical output power, P mechanical, it will be I2 dash whole square into R2 dash into 1 by S minus 1. This will be the mechanical power. So I hope now things are more clearer now. Remember, all these is per phase, right? For 3 phase, you will just simply multiply 3. That's it. But one thing to note here, for the circuit 1, right? The power factor for the circuit 1, if I see, it is what? It is basically tan inverse of XL minus divided by R, right? Tan inverse of XL divided by the resistance. So in the first case, if I see, XL is this S into X2S, right? It is S into X2S divided by, basically the equivalent impedance will not change. If I see the equivalent impedance, mostly it will, okay, it will change basically because it is R2 by S. You will see the power factor angle will not change. It is SX2 divided by R2 simply, right? And in the second case, it is simply this time I have only X2S here and I have R2 divided by S, right? X2S here, I have R2 divided by S. So this value comes out to be tan inverse S X2S divided by R2. Okay. So you see the power factor is same. Power factor is same. Okay. But the thing is, this power input was wrong, right? So actually that's why we converted into this format. That is easier for us. So same thing is written over here, whatever we discussed. The input power, this is the power input, this is only the rotor copper loss, and okay, this is the rotor copper loss. And what is the mechanical power output? Mechanical power output, P mechanical, was I2 whole square into R2 1 by S minus 1, right? This was the mechanical power. So basically what is happening is, first I have stator. From the stator gives some rotating magnetic field. So that field is actually known as the air gap power. Okay, that field is known as the air gap power. So what is the air gap power? Air gap power will be equals to the rotor copper loss plus the mechanical power, right? So what is rotor copper loss? Rotor copper loss is this, right? Sorry, rotor copper loss is this, I2 whole square into R2, and the mechanical power is I2 whole square into R2 1 by S minus 1. So from here you are able to see what is the air gap power. What is the air gap power? So the air gap power, this we will see, don't worry, the power flow we will see more in the next lecture. Air gap power from here I can observe it is simply equals to I2 whole square into R2 divided by S. So it is basically the rotor copper loss divided by S. Okay, there is a very famous equation. So the air gap power, right, P air gap is simply rotor copper loss divided by S. So this is the air gap power. Now what is the mechanical power? Can I write it in terms of, can I write the mechanical power in terms of the air gap power? So air gap power is I2 R2 whole square divided by S. So if I multiply S on both sides, so I can get this equation that I2 whole square R2 is equals to S into P air gap or P input. If they are here saying they are P input, that both are almost similar. Now what I can say is that I can replace here this equation with SPR. If I replace SPR, what I will get, that P mechanical, if I replace with S into PR, so S will come here, S will go inside this bracket, it will be S times 1 by S, that is 1 minus S, right? So it will basically become P air gap into 1 minus S. So very famous relation we get, that the ratio of P air gap is to P rotor copper loss is to P mechanical, the mechanical output power that I will receive. Of course, after receiving the mechanical output power, there are friction, windage losses, all those losses are there. This will be like, this is very important. Numerically, this is very important. This is equals to 1. If the air gap power is 1, then the rotor copper loss will be a ratio of S, right? Because what is my rotor copper loss? If you see, what is my rotor copper loss? My rotor copper loss, P rotor copper loss, is simply S times P air gap. That's why it is S here over here, and the air gap power is 1 minus S. Okay, so 1 is to S is to 1 minus S. So this is basically the ratio. Okay, so yeah, this is a summary, you can go through it. I have just drawn the like equivalent circuit. All this is just for equivalent circuit. Actually in the circuit things are different, right? But I have changed the circuit very much for our easy analysis. Okay, so that's it basically for this lecture. We will continue with this point in the next lecture, this ratio and power flow, how the power flow happens. I have just given you a bit of overview and the equivalent circuit of the rotor. Please remember, all the quantities all the quantities are per phase. So let's say if I want to find out the three phase power, right? If I want to find out the three phase power, what will I do? I will simply multiply 3 into per phase power. Okay, please keep this in mind. Why can I simply multiply 3 into per phase power? Because I know this thing. I know this, that because the system will be balanced, because I'm providing a balanced three phase supply. So I can simply multiply 3 into per phase power, and that will give me the three phase power. Okay, so yeah, this is the key takeaway I want to give you with, and in the next lecture we will see about the power flow equations. So if you have enjoyed this lecture, make sure to hit the like button, make sure to comment down below whatever you feel like, whatever doubts you have, and any appreciation if you want to give. So I will meet you in the next lecture. Until then, happy learning.